50 Mathematical Ideas You Really Need to Know by Tony Crilly. This is an independent educational overview, enriched with our own integrative analysis and actionable exercises. Think of it as a guided reflection to spark your own insights, not a replacement for reading the book itself. 0. Our initial journey into numbers introduces us to counting concrete things. Yet the profound idea of nothing as a quantifiable entity remained largely unaddressed by ancient civilizations like the Greeks and Romans, who lacked a symbolic representation for its absence. The adoption of zero evolved over millennia. Early forms appeared with the Maya, and astronomer Ptolemy used a placeholder symbol. However, it was the 7th century Indian mathematician Brahmagupta who truly defined zero as a number, establishing foundational arithmetic rules that were later introduced to the Western world by Leonardo of Pisa, Fibonacci, in his influential Liber Abaci. Zero integrates seamlessly into addition, 7 plus 0 equals 7, and multiplication, 7 times 0 equals 0. And expands subtraction to encompass negative numbers. 0 minus 7 equals negative 7. The primary challenges emerge with division. While dividing 0 by a non-zero number yields 0, 0 divided by 7 equals 0, attempting to divide by 0, e.g. 7 divided by 0, creates an inherent contradiction. 0 equals 7, rendering it undefined. The case of 0 divided by 0 is indeterminate, as it could logically represent any number. Consequently, for consistent arithmetic, division by 0 is universally excluded. Nevertheless, 0 is an indispensable cornerstone of modern understanding. It is a critical placeholder in our decimal system, allowing for the expression of both astronomically large and infinitesimally small values. Scientifically, it anchors concepts such as longitude, temperature scales, and energy levels. Beyond its practical applications, 0 holds a privileged position on the number line, separating positive from negative numbers, and stands as one of humanity's most significant intellectual achievements, akin to the fundamental empty set in modern set theory. Chapter 2. Number Systems. Number systems represent the fundamental methods by which humanity has quantified the world. Across diverse cultures and eras, these systems evolved from simple tallies to complex mathematical notations. For instance, the ancient Sumerians and Babylonians, inhabiting Mesopotamia approximately 4,000 years ago, developed a place value system based on 60, remnants of which endure in our modern measurements of time and angles. The Egyptians, around the 13th century BC, utilized a base 10 system with hieroglyphs and innovated in handling fractions. However, the widely adopted Hindu-Arabic decimal system, later refined from Babylonian and Hindu origins, proved revolutionary. Its distinct advantage lies in its place value notation and the inclusion of 0, allowing for effortless computation of both incredibly small and immensely large numbers using just 10 numerals, 0 through 9, and powers of 10. This efficiency stands in stark contrast to earlier systems. Consider the Roman numeral system, which employed symbols like I, V, X, L, C, D, M. While suitable for their basic needs, it lacked a 0 and rendered complex arithmetic profoundly challenging, often requiring specialized skill or mental parsing. Even simple addition or multiplication became an arduous task without first converting to decimal. Historical anecdotes, such as King Louis XIV's preference for III over IV on clocks, highlight its unique quirks and inconsistent application. The decimal system expresses numbers like 394 as a sum of powers of 10, 3 times 10 squared plus 9 times 10 first plus 4 times 10 0. This principle extends to fractions using negative powers of 10, seamlessly integrating into decimal notation. for example, 0.572. For numbers of extreme magnitude or minuteness, scientific notation, for example 1.7 times 10 to the 77, provides a concise and practical representation, a feat impossible with Roman symbols. While base 10 dominates everyday life, specialized applications like modern computing rely on alternative bases. The binary system, base 2, using only 0 and 1, is the bedrock of digital technology. Though it can result in lengthy number expressions, its simplicity is crucial for electronic processing. Other bases, such as octal, base 8, and hexadecimal, frequently appear in computing contexts to offer more compact representations than binary, bridging the gap between human readability and machine efficiency. 3. Fractions. A fraction, in essence, is a portion of a whole, a fractured number that allows us to precisely quantify parts. Every fraction consists of a numerator atop a denominator. The denominator indicates how many equal parts constitute the whole, while the numerator reveals how many of those parts are being considered. For instance, if a cake is divided into 3 equal slices and you take 2, you possess 2/3 of the cake, where 3 is the denominator, total parts, and 2 is the numerator, parts taken. Fractions come in various forms. Proper fractions have a numerator smaller than the denominator, like 2/3, while improper fractions have a numerator equal to or larger, e.g. 14/5. An improper fraction can be expressed as a mixed number, combining a whole number and a proper fraction, like 2 4/5. For clarity and simplicity, fractions are typically presented in their simplest form, meaning the numerator and denominator share no common factors other than 1. For example, 8/10 simplifies to 4/5 by canceling the common factor of 2. Performing operations on fractions requires distinct approaches. Multiplication is straightforward. Simply multiply the numerators together and the denominators together. For example, 1/2 times 4/5 becomes 2/10, which simplifies to 1/5. Addition, however, is more intricate. Fractions can only be added directly if they share the same denominator. If they do not, you must first find a common denominator by adjusting each fraction, typically by multiplying both its numerator and denominator by the other fraction's original denominator. Once common, the numerators can be summed. Fractions can also be expressed as decimals, which are particularly common in scientific contexts. To convert a fraction to a decimal, divide the numerator by the denominator. This process may result in a terminating decimal, e.g. 7/8 equals 0.875, or a recurring decimal, where a sequence of digits repeats infinitely, e.g. 2/3 equals 0.666, often written as 0.6 with a bar. Chapter 4. Squares and Square Roots. To understand the core concepts of squares and square roots, we can look back to the ancient Pythagoreans, a Greek fraternity who believed mathematics held the key to the universe's nature. They particularly enjoyed arranging dots into geometric patterns. Consider arranging dots to form squares. The first square has 1 dot. The next, a 2x2 arrangement, has 4 dots. Continuing this, we get square numbers, or perfect squares, 1, 4, 9, 16, 25, and so on. These numbers can be found by adding the sequence of odd numbers. For example, 1 plus 3 equals 4, 4 plus 5 equals 9, 9 plus 7 equals 16. The Pythagoreans also explored triangular numbers, formed by dots arranged in triangles, like piles of stones. These are 1, 3, 6, 10, 15, etc., where each number is found by adding the next consecutive integer to the previous triangular number, e.g., 1 plus 2 equals 3, 3 plus 3 equals 6. A fascinating connection emerges between these types of numbers. Adding any two successive triangular numbers always results in a perfect square number. For instance, 3 plus 6 equals 9, or 10 plus 15 equals 25. This can be visually proven by fitting two successive triangular dot patterns together to form a square. Moving from these dot diagrams to formal geometry, the area of a square with side length x is x squared, written as x squared. This mathematical relationship forms the basis for the parabolic shape, prevalent in nature and technology. Parabolas are seen in satellite dishes, where parallel signals converge at a focal point, or in car headlights, where a light source at the focus emits a parallel beam. In sports, the path of a thrown object, like a javelin or shot put, also traces a parabola as it falls. Turning the concept around, if we know the area of a square, finding its side length is called taking the square root. For example, the square root of 16 is 4, written as square root 16 equals 4. All perfect squares have whole numbers as their square roots. However, many numbers like 2, 3, 5, or 7 do not have whole number square roots. Their square roots are often approximations, even when calculated to many decimal places. The square root of 2, sometimes called the Pythagorean number, is a prime example. No matter how many decimal places we compute, we only get closer to its true value. We never find an exact, terminating, or repeating decimal representation. This leads to a profound question posed by the ancient Greeks. Can all lengths be measured as a ratio of whole numbers, or a fraction? They believed any measurable length could ultimately be expressed as m over n. However, root 2 defied this belief. Through a brilliant method known as reductio ad absurdum, proof by contradiction, they demonstrated that root 2 cannot be a fraction. The proof starts by assuming root 2 is a fraction, m over n, where m and n have no common factors. Squaring both sides shows that m squared equals 2n squared, implying m squared is even, which in turn means m must be even. If m is even, we can write it as 2k. Substituting this back into the equation reveals that n squared equals 2k squared, meaning n squared is also even, and thus n must be even. This creates a contradiction. If both m and n are even, they share a common factor of 2, which violates our initial assumption that m and n had no common factors. Therefore, the initial assumption must be false. Root 2 cannot be a fraction. Numbers like root 2, which cannot be written as a ratio of two integers, are termed irrational numbers, revealing that the number line contains infinitely many values beyond simple fractions.
05. Pi. Pi stands as mathematics' most celebrated number, a constant woven into the very fabric of circles and spheres, yet appearing in countless unexpected mathematical contexts. Fundamentally, pi represents the unchanging ratio of a circle's circumference to its diameter, holding steady regardless of the circle's size. This versatility means pi is key to fundamental geometric formulas. A circle's circumference is pi d, or 2 pi r. Its area is pi r squared, while for a sphere, the surface area is pi d squared, or 4 pi r squared, and volume is 4/3 pi r cubed. The journey to understand pi began millennia ago, with ancient civilizations like the Babylonians approximating its value. Around 225 BC, Archimedes of Syracuse, a titan among mathematicians, made the first rigorous strides. He ingeniously bounded pi's value between two fractions, 22/7 and 223/71, by inscribing and circumscribing polygons around a circle, cementing 22/7 as a familiar approximation. Though William Jones introduced the pi symbol in the 18th century, Leonhard Euler championed its widespread adoption. Later, Ferdinand von Lindemann's 1882 proof that pi is transcendental, meaning it cannot be the solution to any algebraic equation, finally settled the ancient squaring the circle problem, conclusively demonstrating its impossibility using only a compass and straightedge. Pi's true nature as an irrational number, proved by Johann Lambert in 1768, means its decimal expansion is infinite and never repeats, in a predictable pattern, e.g. 314, 1592, 635, 8972, etc. This endless sequence fuels a modern fascination with calculating pi to ever more decimal places, from William Schenk's 19th century efforts to supercomputers reaching trillions of digits today. These colossal computations serve not just intellectual curiosity, but also push the boundaries of computer capabilities. While only a few decimal places suffice for most practical applications, pi's profound properties and the quest to uncover patterns within its digits continue to captivate mathematicians, showcasing humanity's enduring drive to understand the cosmos through numbers.
While the venerable constant pi boasts an ancient lineage, E emerges as its more recent, dynamic counterpart, inherently linked to the concept of growth. Approximating 2.7182, E isn't a random figure, but a cornerstone of mathematics, first illuminated in the early 17th century during efforts to understand logarithms. The true narrative of E unfolds with Jacob Bernoulli's 1683 exploration into compound interest. Consider an initial deposit of £1 at an astonishing 100% annual interest. If compounded annually, the sum becomes £2. However, if that 100% is split and applied semi-annually, 50% per half year, the £1 grows to £2.25. Dividing the year further, say into 4 quarters with 25% interest each, yields 2.44141. This continuous subdivision of the compounding period illustrates a profound principle. As the intervals become infinitesimally small, the total amount approaches a fixed limit. This limit, which mathematicians denote as E, represents the sum £1 grows to under continuous compounding. This phenomenon reveals E's fundamental role in modeling continuous growth across population dynamics to financial accrual. Like pi, E is an irrational number, meaning its decimal representation never ends or repeats. Beyond its approximate value, E possesses a precise definition through an infinite series involving factorials. This mathematical elegance hints at a symmetric quality often contrasted with pi's nature. Historically, Leonhard Euler proved E's irrationality in 1737, while later mathematicians Liouville and Hermite progressively demonstrated its transcendental nature, meaning it isn't the solution to any algebraic equation. This makes E an exceptionally profound constant. Fascinatingly, E and pi also exhibit intriguing relationships, such as the inequality e to the pi is greater than pi to the e, and e to the pi forming Gelfand's constant known to be transcendental. E's importance extends far beyond financial growth. It models radioactive decay, appears in probability theory, like the Montmort problem of hats picked randomly, yielding a probability of 1 over E for no one getting their own, in statistics with the omnipresent bell curve of the normal distribution, and in engineering, defining the curve of suspension bridge cables. But perhaps E's most celebrated appearance is in Euler's identity, e to the I pi plus 1 equals 0. A formula that elegantly connects 5 fundamental constants of mathematics, 0, 1, pi, e, and I, equals the square root of -1. This identity is widely regarded as one of mathematics' most beautiful and profound truths, solidifying E's unavoidable presence across the mathematical landscape. 07. Infinity.
Infinity, often symbolized as infinity, represents a concept of endless growth where for any colossal number, an even larger one always exists. Traditionally, this suggests a boundless linear progression. However, in mathematics, infinity demands careful treatment, as it isn't an ordinary number. The German mathematician Georg Cantor revolutionized our understanding of infinity by introducing a more profound system of counting based on one-to-one correspondence. Imagine a farmer, unaware of numerical counting, who uses stones to match each sheep returning to its pen. If a stone remains, a sheep is missing. This primitive method, establishing a one-to-one relationship, forms the bedrock of Cantor's set theory. A set is simply a collection of objects, like the set of positive whole numbers n equals 1, 2, 3, etc. Surprisingly, through this correspondence, Cantor demonstrated that the set of odd numbers 1, 3, 5 has the same number as the set of even numbers 2, 4, 6. Even more astonishing, the entire set of whole numbers n shares the same size as its subset, the even numbers, a conclusion that challenged ancient Greek notions that the whole must be greater than its part. The number of elements in a set is termed its cardinality. For the whole numbers and any set that can be put into one-to-one correspondence with n, Cantor introduced the symbol aleph naught. Such sets are called countably infinite, implying their elements can theoretically be listed sequentially. Remarkably, even the set of all fractions, q, which includes positive and negative values, can be shown to be countably infinite. By arranging fractions in a two-dimensional grid and then following a clever zigzag path, every fraction can be assigned a unique position on a linear list, proving card q equals aleph naught. However, the real number line, r, which includes irrational numbers like square root 2 and pi that fill the spaces between fractions, presents a different scale of infinity. Cantor's brilliant diagonalization argument demonstrated that the real numbers, even just those between 0 and 1, cannot be arranged into a list. By constructing a new real number that differs from every number on any hypothetical list in at least one decimal place, he proved that no such comprehensive list is possible. This means the set of real numbers possesses a higher order of infinity than the countably infinite sets, revealing that not all infinities are equal. Some are demonstrably bigger. 8. Imaginary numbers. While we often associate imaginary with fanciful daydreams of wealth, in mathematics, these numbers refer to distinct, non-ordinary solutions to equations. Coined by René Descartes, the term imaginary sparked philosophical debate about their existence. For mathematicians, however, imaginary numbers are as fundamental as 5 or pi, proving indispensable in fields like aircraft design and electrical engineering. When combined with a real number, they form a complex number, a less intimidating term for a revolutionary concept built around the square root of -1. Ordinarily, squaring any non-zero real number yields a positive result. This fundamental rule presented a significant hurdle for centuries when trying to find a number that, when squared, equals -1. The breakthrough came with the bold acceptance of root -1 as a new mathematical entity, denoted as I. This single conceptual leap expanded the number system from a one-dimensional line to a rich two-dimensional plane, liberating mathematics from previous constraints and opening vast new avenues of inquiry. Complex numbers, expressed in the form a plus bi, adhere to familiar arithmetic operations. Addition involves combining their respective real and imaginary components. Multiplication works by distributing terms, remembering that I squared simplifies to -1. While complex numbers share most properties with real numbers, they cannot be categorized as simply positive or negative. Their two-dimensional nature is vividly displayed on an Argand diagram, where each complex number corresponds to a point in a plane, with one axis for real parts and another for imaginary parts. Each complex number also possesses a conjugate, e.g., the conjugate of 1 plus 2i is 1 minus 2i, formed by reversing the sign of its imaginary component. Notably, adding or multiplying a complex number by its conjugate always results in a real number. This multiplication also defines the length of a complex number, which can be visualized as its distance from the origin on the Argand diagram. The formal understanding of complex numbers was furthered by Sir William Rowan Hamilton, who demonstrated that the symbol I itself was not strictly necessary. Complex numbers could be represented as ordered pairs of real numbers, a, b, reinforcing their two-dimensional essence. This expanded system also elegantly handles concepts like the nth roots of unity, solutions to Zn equals 1. For instance, Z6 equals 1 has 6 roots, all lying on the unit circle of the Argand diagram and forming the vertices of a regular hexagon. Driven by an impulse for generalization, mathematicians sought to extend complex numbers into higher dimensions, successfully developing 4-dimensional quaternions and 8-dimensional Cayley numbers, though the pursuit of 16-dimensional counterparts ultimately proved impossible.
9. Primes. Mathematics, at its core, relies on prime numbers, unbreakable integers divisible only by 1 and themselves, e.g., 2, 3, 5. These form the fundamental atoms from which all other composite numbers are uniquely constructed, a principle solidified by the prime number decomposition theorem. While early methods like Eratosthenes' sieve identified them, their distribution remains elusive. Carl Friedrich Gauss's estimation formula for prime numbers, despite its utility, demonstrates unexpected fluctuations across large number ranges, underscoring their unpredictable nature. Euclid's elegant proof confirmed the infinitude of primes, ensuring an endless supply. Yet significant mysteries persist, including the twin primes problem, questioning if there are infinitely many pairs like 11, 13. And Goldbach's conjecture, proposing every even number greater than 2 is the sum of 2 primes. These enduring puzzles, though unproven, highlight the depth of number theory, extending even to concepts like Gaussian integers, where primes can exhibit further factorization. Intriguingly, numbers like 666 illustrate profound numerical properties, such as being the sum of the squares of the first 7 primes, connecting different mathematical realms. Chapter 10. Perfect Numbers. In mathematics, a perfect number is a positive integer where the sum of its proper divisors, excluding itself, precisely equals the number. For instance, 6 has divisors 1, 2, and 3, which sum to 6. This contrasts with deficient numbers, where the sum of divisors is less than the number, e.g. 26, and superabundant numbers, where the sum is greater than the number, e.g. 30. The earliest known perfect numbers are 6, 28, and 496. A significant insight, formalized by Euclid and Euler, links all even perfect numbers to Mersenne primes, prime numbers of the form 2n minus 1. Specifically, an even perfect number is always generated by the formula 2 to the p minus 1 times 2 to the p minus 1 when 2 to the p minus 1 is a Mersenne prime. This formula underscores that discovering new even perfect numbers directly depends on identifying new Mersenne primes. Beyond perfect numbers, other intriguing relationships exist, such as amicable numbers, e.g. 220 and 284. The elusive odd perfect number remains one of mathematics' oldest unsolved problems. Despite extensive investigation, none have ever been found, leading many experts to doubt their existence. Chapter 11. Fibonacci Numbers.
The Fibonacci sequence, celebrated as one of mathematics' most famous numerical patterns, begins with 1, 1 and proceeds by adding the two preceding numbers to generate the next, e.g., 1, 1, 2, 3, 5, 8. This fundamental characteristic governs its pervasive appearance across nature, from the spirals of sunflowers and pine cones to architectural design principles and musical compositions. Its origins are famously traced to Leonardo of Pisa, Fibonacci, in the 13th century, who used a problem about hypothetical rabbit populations to illustrate this very growth pattern, where the total number of pairs each month follows the sequence. Beyond its basic definition, the sequence reveals intriguing properties, such as predictable patterns in the sums of its terms and even its unexpected emergence in counting arrangements, like the various ways to combine different coin denominations to reach a specific sum. As the sequence progresses, the ratio of any term to its predecessor remarkably approaches a constant known as the golden ratio, phi, a revered mathematical constant valued at approximately 1.618. This sequence is also part of a larger family of related number patterns, like the one describing cattle population growth, which similarly generates its own unique super-golden ratio, demonstrating the enduring mysteries and elegant interconnections within numerical systems. 12 golden rectangles. Rectangles surround us in daily life, from architecture to art, subtly influencing our visual landscape. This ubiquity raises a question. Is there an ideal rectangle, one universally considered most aesthetically pleasing? Many believe so, with the golden rectangle often championed for its unique proportions. Consider the common A-size paper, like A4. Its length-to-width ratio is approximately 1.4142. A remarkable property of this system is that when an A-size sheet is folded precisely in half, the two resulting smaller rectangles maintain the exact same proportions as the original. Mathematically, if a rectangle has breadth 1 and length x, then upon halving, the smaller rectangle has breadth half x and length 1. For these ratios to be identical, x over 1 must equal 1 over half x, leading to x squared equals 2, meaning x is the square root of 2. The golden rectangle shares a similar self-replicating characteristic, but with a subtle difference. Instead of folding in half, imagine a golden rectangle from which a square is removed from one end. The critical feature is that the remaining, smaller rectangle is perfectly proportional to the original large one. If the breadth of the original rectangle is 1 and its length x, then removing a square of side 1 leaves a smaller rectangle with breadth x minus 1 and length 1. For their proportions to match, x over 1 must equal 1 over x minus 1, which simplifies to the equation x squared equals x plus 1. The positive solution to this equation is approximately 1.618, a renowned constant known as the golden ratio, denoted by the Greek letter phi. Building a golden rectangle begins with a simple square. By finding the midpoint of one side, drawing a line to an opposite corner, and using Pythagoras' theorem, one can extend the original square to form a rectangle whose longer side is precisely the golden ratio. While mathematically elegant, the golden ratio has often been over-attributed in art and architecture, a phenomenon dubbed golden numberism. For instance, claims that the Parthenon perfectly embodies the golden ratio are debatable, as different interpretations of its dimensions yield varying ratios. Nevertheless, throughout history, thinkers have been captivated by it. Luca Pacioli, a contemporary of Leonardo da Vinci, christened it the divine proportion in 1509. Later, psychologist Gustav Fechner observed that many everyday rectangular objects tend to approximate this ratio. Modern architects like Le Corbusier intentionally integrated golden rectangles into their designs, recognizing their aesthetic appeal and harmonious qualities. Beyond the golden rectangle, other fascinating proportional shapes exist, such as the super-golden rectangle. Its construction is conceptually related, but involves a more complex geometric relationship that leads to a cubic equation, x cubed equals x squared plus 1. The solution, approximately 1.4657 psi w, defines this rectangle, but unlike the golden rectangle, it cannot be precisely constructed using only a straight edge and compasses.
Chapter 13. Pascal's Triangle. Pascal's triangle is a remarkable mathematical structure celebrated for its profound symmetry and interconnected patterns. Although named for Blaise Pascal, who explored it in 1653, its underlying principles were understood by Chinese scholars centuries earlier. It builds quite simply. Begin with a 1 at the very top. Then each subsequent row starts and ends with 1. All internal numbers are generated by summing the two numbers positioned directly above them. This elegant construction reveals deep connections throughout mathematics. Algebraically, the numbers within the triangle correspond precisely to the coefficients found in binomial expansions, such as those arising from 1 plus x raised to the n. A fascinating property is that summing the numbers in any given row consistently yields a power of 2. Beyond these, the triangle's diagonals house sequences like the simple counting numbers, triangular numbers, which form triangular of dots, and tetrahedral numbers, representing dots in a 3D triangular pyramid. Even more compelling, if one sums numbers along specific, almost diagonals, the renowned Fibonacci sequence emerges when these sums are properly interleaved. Visually, substituting odd numbers with 1 and even numbers with 0 throughout the triangle generates a striking fractal pattern known as the Sierpinski gasket. The triangle also provides a straightforward method for calculating combinations, such as choosing r items from a set of n, C n, r, illustrating its practical power in counting possibilities. Pascal's triangle stands as a vivid example of the deep patterns and harmony inherent in the mathematical universe. Chapter 14. Algebra. Algebra offers a unique problem-solving approach, famously employing backwards thinking. Instead of just calculating outcomes, it allows us to uncover unknown values by setting up equations. Early applications involved practical word problems, efficiently solving what might otherwise require trial and error. Mathematics progressed significantly as it embraced symbols, moving beyond simple linear equations to quadratic, involving x squared, cubic, x cubed, and quartic, x4 forms, all solvable with general formulas. A major 19th century discovery by Niels Abel, however, proved that no universal formula exists for quintic equations, x5, a profound revelation about mathematical limits. In the modern era, algebra expanded beyond numerical unknowns. William Rowan Hamilton's 1843 discovery of quaternions, a system where multiplication order matters, exemplified new abstract structures. This led to abstract algebra, championed by Emmy Noether, which studies underlying structures like groups and fields, exploring how mathematical entities behave based on inherent properties. Chapter 15. Euclid's Algorithm. An algorithm, a term derived from Al-Khwarizmi's 9th century work, is fundamentally a precise sequence of instructions, or a routine. Far from being tedious, crafting an effective algorithm is a creative challenge, demanding efficiency and accuracy, much like perfecting a recipe. In mathematics, these ingredients are often numbers, and Euclid's algorithm offers an elegant method for finding the greatest common divisor, GCD, of two whole numbers, the largest number that divides both without a remainder. For instance, the GCD of 18 and 84 is 6, interpretable as the side length of the largest square tile that can perfectly cover an 18 by 84 rectangle. While prime factorization can find the GCD, it quickly becomes cumbersome for larger numbers.
Euclid's algorithm streamlines this process by employing repeated division. To find GCD 8418, one divides 84 by 18, yielding a remainder. 84 equals 4 times 18 plus 12. The key insight is that the GCD of the original numbers is the same as the GCD of the smaller number and the remainder, i.e. GCD 1812. This process repeats. 18 equals 1 times 12 plus 6. Then 12 equals 2 times 6 plus 0. The last non-zero remainder, 6, is the GCD. This powerful technique also finds use in solving Diophantine equations, those requiring whole number solutions. For such an equation, like 18x plus 84y equals c, a solution exists if and only if the GCD of 18, which is 6, divides c. Furthermore, when two numbers have a GCD of 1, they are called relatively prime. This concept is crucial for the Chinese remainder theorem. This theorem solves problems where a number is known only by its remainders when divided by several different numbers. For example, if Angus has bottles that leave a remainder of 1 when divided by 2, 3 when divided by 5, and 3 when divided by 7, the theorem guarantees a solution, like 73, and explains that all other solutions differ by multiples of 2 times 5 times 7, or 70.
16. Logic. Logic provides a rigorous method for assessing argument validity, separate from factual accuracy. Aristotle's foundational work introduced syllogisms, arguments with two premises and a necessary conclusion. Their validity resides in their structure, not their content. A valid syllogism ensures a true conclusion if premises hold. Conversely, a counterexample proves invalidity. Expanding beyond syllogisms, propositional logic, developed by thinkers like Boole, examines propositions, simple true-false statements, and their combinations using connectives like or, and, not, say. Implies, I3, is another key connective, false only when its premise is true and its conclusion false. This framework allows precise analysis. For instance, to validate a complex argument like the newspaper editorial, we symbolize its statements. By assuming its conclusion is false while all premises are true, and then showing this leads to a contradiction, we confirm its inherent validity, irrespective of the subject matter's actual truth. Modern logic continues to evolve, encompassing predicate logic with quantifiers and fuzzy logic, which precisely models uncertainty, underscoring its vibrant role in contemporary thought. Chapter 17. Proof. Mathematical progress hinges on rigorous proofs, logical deductions from established facts to new conclusions, providing authenticity to theorems. Essential proof qualities include rigor, clarity, elegance, and insight. Key methods of proof include the counterexample, which disproves a universal statement with a single contradictory instance. Example, 9 squared equals 81, disproves all squared numbers are even. The direct method, advancing logically from premise to conclusion. Example, showing an even number 2k squared as 2k squared is always even. The indirect method, or reductio ad absurdum, where one assumes the opposite of the conclusion, then derives a contradiction, thereby affirming the original statement. Example, proving root 2 is irrational. Mathematical induction, a domino effect method for proving sequences of statements Pn true for all whole numbers. It requires showing P1 is true and that Pk implies Pk plus 1 is true. Example, proving the sum of the first n odd numbers is n squared. Proofs vary greatly in length and complexity, with some challenging human comprehension. Foundational debates persist, like those between constructivists, who demand explicit constructions for existence proofs, and classical mathematicians, who value indirect methods like reductio ad absurdum as essential.
Chapter 18. Sets. Set theory, conceived by George Cantor, established a mathematical foundation through the concept of sets, collections of distinct elements. Basic operations include union, elements in either set, intersection, common elements, and complement, elements outside a set within a universal context, forming an algebra of sets governed by principles like De Morgan's laws. However, the initial informal definitions, especially for infinite sets, led to logical quandaries, like Bertrand Russell's paradox, demonstrating how self-reference could create irreconcilable contradictions. This necessitated formal axiomatic systems, such as the Zermelo-Fraenkel axioms, designed to rigorously define set properties and prevent such paradoxical constructions by limiting what constitutes a valid set. Despite these efforts to create a complete foundation, Kurt Gödel's incompleteness theorem revealed that any sufficiently complex axiomatic system contains undecidable statements, truths unprovable or undisprovable from within its own rules. Concurrently, Cantor distinguished various orders of infinity, demonstrating that real numbers represent a higher infinity, C, than rational numbers, a left not. The continuum hypothesis, positing the specific relationship between these infinities, was ultimately shown by Paul Cohen to be independent of the Zermelo-Fraenkel axioms, allowing for different foundational interpretations of set theory. 19. Calculus. Calculus, a central pillar of mathematics, was pioneered by Isaac Newton and Gottfried Leibniz in the 17th century. Its core consists of two inverse operations, differentiation and integration. Differentiation quantifies instantaneous change, like determining the precise speed of a falling object at a given moment. It operates by examining changes over infinitesimally small intervals, transforming a distance function y equals 16x squared into a velocity v equals 16 times 2x. Where 2x is the derivative of x squared. This process of finding the derivative was a groundbreaking step in measuring dynamic processes. Integration, on the other hand, measures the total accumulation or area under a curve. This is achieved by conceptually summing an infinite number of tiny rectangular strips. For instance, integrating x squared yields x cubed by 3. The profound connection, the fundamental theorem of calculus, reveals that differentiation and integration are perfect inverses. This foundational understanding allows for analysis wherever continuous change occurs, profoundly influencing fields from orbital mechanics to economics. 20 constructions. Ancient Greek mathematicians, armed only with a straightedge and compass, grappled with 4 renowned construction challenges, often culminating in profound proofs of impossibility. This quest, demanding extraordinary ingenuity within strict limitations, saw solutions only fully emerge through modern analysis centuries later. 3 of these problems proved largely insurmountable. While bisecting any angle is straightforward using the basic tools, trisecting an arbitrary angle, like a 60-degree angle, is fundamentally impossible. Similarly, the Delian problem of doubling a cube's volume required constructing a precise length equal to the cube root of 2, a feat geometrically impossible with a straightedge and compass. Most famously, squaring the circle, creating a square with equivalent area, was definitively proven impossible by Ferdinand von Lindemann. His work demonstrated that the constant pi is a transcendental number, meaning it cannot be the root of any algebraic equation, thus placing it beyond constructability with these classical instruments. Amidst these constraints, one area offered a remarkable triumph of possibility: constructing regular polygons. Euclid had outlined methods for polygons up to 6 sides. However, it was Carl Friedrich Gauss who made a truly significant breakthrough as a teenager. He proved that a p-sided regular polygon, where p is a prime number, is constructible if and only if p is a Fermat prime, a prime number of the form 2 to the second n plus 1. This mathematical revelation unveiled the constructability of shapes like the 17-sided polygon, showcasing a profound expansion of geometric understanding. Chapter 21. Triangles. A triangle, a fundamental three-sided figure, forms the core of trigonometry, the branch of mathematics dedicated to measuring its properties. Key principles include the angle sum of 180 degrees in any flat triangle, a fact elegantly proven through parallel lines, and Euclid's triangle inequality, asserting that the combined length of any two sides always exceeds the third. The most famous is Pythagoras' theorem. In a right-angled triangle, the square of the hypotenuse, c squared, equals the sum of the squares of the other two sides, a squared plus b squared, a concept often visualized through geometric proofs. Triangles also possess intriguing centers: the centroid, center of gravity, orthocenter, where altitudes meet, and circumcenter, center of a circumscribed circle, which universally align on the Euler line. Further complexities arise in theorems, like Napoleon's, where constructing equilateral triangles on each side of any triangle and joining their centers produces another equilateral triangle. Practically, triangles are indispensable. Surveyors use triangulation for mapping vast regions, like India's Great Trigonometrical Survey. Engineers exploit their inherent rigidity in stable structures, such as trusses and Warren girder bridges. Finally, Heron's formula allows calculating a triangle's area from side lengths alone, showcasing its profound and widespread utility.
22. Curves. Despite their prevalence in art, architecture, and nature, precisely defining a curve is a surprisingly complex endeavor that has fascinated mathematicians for centuries. Early investigations by the Greeks introduced classical curves, most notably the conic sections, the circle, ellipse, parabola, and hyperbola. These are formed by slicing a double cone at various angles or by tracing points whose distances from fixed points or lines meet specific criteria. For instance, Johannes Kepler famously revealed that planets follow elliptical orbits, while parabolas are crucial for focusing light or signals. Beyond these, spirals, like the logarithmic spiral revered by Bernoulli and seen in DNA's double helix, and curves such as the heart-shaped cardioid and the chain-forming catenary also belong to this classical family. The 19th century further explored mechanical curves generated by moving rods like the sextic curves from three-bar mechanisms. A significant shift occurred with René Descartes' introduction of coordinate geometry, allowing curves to be studied as algebraic equations. A simple circle, for example, could be represented as x squared plus y squared equals 1. This led to algebraic geometry, with Isaac Newton classifying 78 types of cubic curves. However, not all curves, such as cycloids or catenaries, are easily expressed algebraically. The quest for a universal definition continued with Camille Jordan, who proposed defining a curve as a path traced by variable points, parametric equations. His simple closed curve theory, positing an inside and an outside, seemed foundational until Giuseppe Peano, in 1890, presented a space-filling curve, a square that, by Jordan's definition, was also a curve. This revelation exposed the limitations of existing definitions, propelling mathematics into the new frontier of topology to fundamentally rethink the nature of curves.
Chapter 23. Topology. Topology is a unique branch of geometry that explores the intrinsic properties of shapes and surfaces, disregarding precise measurements of length or angles. Often called rubber sheet geometry, it focuses on qualities that remain unchanged even when a shape is stretched, bent, or twisted, but not torn or cut. This perspective leads topologists to famously view a donut and a coffee cup as topologically identical, both possessing a single hole. The study of shapes often begins with polyhedra, multi-faced geometric solids. A familiar cube, for instance, has 6 faces, 8 vertices, and 12 edges. Among these, the 5 Platonic solids, tetrahedron, cube, octahedron, dodecahedron, and icosahedron, are distinguished as regular polyhedra, characterized by identical regular faces and equal angles at their vertices. Less rigid are these semi-regular, Archimedean solids, such as the truncated icosahedron, which forms the structure of a soccer ball, and the Buckminster-Fullerene molecule. A fundamental principle in topology is Euler's formula, which states that for any simple polyhedron, the number of vertices, V, minus the number of edges, E, plus the number of faces, F, always equals 2. V minus E plus F equals 2. This formula, however, revealed a deeper complexity when confronted with shapes like a cube containing a tunnel, where the sum becomes 0. This disparity led to a broader understanding. Surfaces can be classified by their number of holes, R, with a generalized Euler characteristic of V minus E plus F equals 2 minus 2R. This characteristic becomes 2 for surfaces without holes, R equals 0, and 0 for surfaces with one hole, R equals 1. Beyond counting holes, topology also investigates surfaces with unexpected properties, such as being one-sided. While typical surfaces like a ball or a piece of paper have distinct inner and outer sides, the Mobius strip, created by twisting a paper strip once before joining its ends, possesses only a single continuous side. Even more remarkable is the Klein bottle, a one-sided surface without a boundary, which theoretically exists without self-intersection in 4 dimensions. Both are examples of manifolds, geometric spaces that locally resemble flat Euclidean space. A profound challenge in topology was the Poincaré conjecture, an algebraic topological problem concerning closed 3 manifolds. It posited that any closed 3 manifold resembling a 3-dimensional sphere, based on its algebraic characteristics, must indeed be a sphere. This complex problem, unyielding for over a century, was finally proven by Grigori Perelman in 2002, using innovative techniques from outside traditional topology, specifically related to heat diffusion.
24-dimension. Echoing Euclid and Leonardo da Vinci, the traditional understanding of dimensions, based on a hierarchy from a 0-dimensional point to 1-dimensional lines, 2-dimensional planes, and 3-dimensional physical solids, long prevailed. For millennia, this conventional view, describing physical space with x, y, z coordinates, defined reality. Yet by the 19th century, mathematicians ventured beyond, exploring abstract n-dimensional mathematics. The notion of higher physical dimensions gained pivotal importance with Einstein's theory of relativity, which unified space and time into a 4-dimensional x, y, z, t continuum, making the concept more plausible. Modern string theories push this further, positing our universe might exist in 10, 11, or even 26 dimensions, with ongoing experiments at CERN seeking to uncover its true nature. In contrast, mathematical hyperspace faces no such physical constraints, seamlessly extending to any number of variables. Mathematicians define entities like 4-dimensional hyperspheres or hypercubes, existing within an ideal, abstract realm. This conceptual journey culminates in spaces of immense complexity, such as the 196,883 dimensions associated with the monster group in symmetry classification. Thus, the concept of dimension has profoundly evolved beyond the simple 1, 2, and 3 of Euclidean geometry. 25. Fractals. In 1980, a profound shift in mathematical exploration unfolded as Benoit Mandelbrot, at an IBM research center, witnessed the accidental birth of the Mandelbrot set on a printer. This marked a new era of experimental mathematics, where visual discovery often preceded formal theoretical frameworks.
Mandelbrot, appreciating the concept's emergent magic, initially resisted a rigid definition for fractals, likening it to a fine wine that required aging before being bottled. The Mandelbrot set itself arises from the remarkably simple iterative formula z squared plus c, applied using complex numbers. It encompasses all those values of c for which the sequence of iterated z values, starting from z equals 0, does not escape to infinity. This process unveils astonishingly intricate and endlessly complex shapes that famously exhibit self-similarity. Magnifying any portion reveals patterns strikingly similar to the whole. While Mandelbrot brought fractals into the mainstream, mathematicians such as Gaston Julia and Pierre Fatou had explored similar structures in the complex plane decades earlier, albeit without the computational power to visualize their hidden depths. Other renowned fractals include the Koch snowflake, which paradoxically encloses a finite area while possessing an infinite perimeter, and the Sierpinski gasket, generated through recursive geometric subtractions. A defining characteristic of fractals is their fractional dimension, formerly known as the household's dimension. Unlike conventional geometric figures, a line with dimension 1, a square with dimension 2, fractals possess non-integer dimensions. For instance, the Koch curve's household's dimension is approximately 1.262. A value reflecting its unique, infinitely jagged complexity. This innovative mathematical property provides a powerful tool for modeling the inherent irregularity and intricate branching patterns found throughout the natural world. Consequently, fractals find wide-ranging applications, from simulating plant growth and cloud formations to analyzing the intricate structures of marine organisms, modeling brain activity, and even understanding the unpredictable dynamics of stock markets and foreign exchange. Mandelbrot's pioneering insights continue to inspire profound new avenues of scientific and mathematical discovery. Chapter 26. Chaos. Chaos theory reveals a universe far more intricate than previously conceived. Contrary to the 19th-century deterministic view of the Marquess de Laplace, which posited that knowing all initial conditions would allow precise prediction of all future states, chaos theory demonstrates that even minute differences in starting points can lead to drastically different outcomes. This phenomenon, famously termed the butterfly effect, suggests that a tiny perturbation, like a butterfly's wing flap, could theoretically alter global weather patterns. This profound sensitivity to initial conditions is evident in simple systems. For instance, releasing a ball bearing repeatedly into a pinboard maze from what seems like the exact same spot will likely yield varied landing slots, due to unmeasurable microscopic differences. Similarly, a simple pendulum's predictable spiraling decay to rest contrasts sharply with the wild, seemingly random motion of a double pendulum, which exhibits erratic lurching despite its deterministic mechanics. The mathematics governing complex systems like weather patterns are often nonlinear, meaning variables are multiplied together, amplifying the impact of tiny inaccuracies over time. While chaotic systems appear random, they are fundamentally deterministic, often exhibiting underlying mathematical structures known as strange attractors, which can be fractals. This implies that even within apparent chaos, there is a regular chaos, a predictable unpredictability that scientists continue to explore. Chapter 27. The Parallel Postulate. Euclid's Elements, penned around 300 BC, established the foundational principles of geometry through 5 seminal postulates. Among these, the fifth, concerning parallel lines, stood out for its complexity and lack of immediate self-evidence. This postulate essentially posited that through a point P not on a line L, there exists one and only one line parallel to L. While seemingly intuitive, this assumption proved a persistent challenge for mathematicians for over 2 millennia, who struggled either to prove it from the other postulates or to find a simpler alternative. Attempts often fell into circular reasoning, assuming what they sought to prove. A revolutionary shift occurred in the 19th century with the independent work of Carl Friedrich Gauss, Janos Bolyai, and Nikolai Ivanovich Lobachevsky. They demonstrated that the fifth postulate was independent of Euclid's other four. By negating it, they paved the way for consistent, alternative geometries, fundamentally reshaping our understanding of space. These non-Euclidean geometries include hyperbolic geometry, where more than one line can pass through point P parallel to line L. This geometry, often visualized on a saddle-shaped pseudosphere, features triangles whose angles sum to less than 180 degrees. Elliptic geometry. Proposed by Bernhard Riemann, this geometry posits that no lines through P are parallel to L. All lines eventually meet. Modeled on the surface of a sphere, where straight lines are great circles, triangles in this geometry have angles that sum to greater than 180 degrees. This paradigm-altering discovery dethroned Euclidean geometry from its status as the sole description of physical space. Instead, it became one of several valid systems, opening doors to profound new mathematical and physical theories. Most notably, non-Euclidean geometry became indispensable for Albert Einstein's general theory of relativity, which explains gravity not as an attractive force, but as the curvature of space-time caused by massive objects. Riemannian geometry, with its concept of continuously varying curvature, provides the mathematical framework for understanding this dynamic, curved universe, revealing how phenomena like light bending occur within this cosmic fabric.
28. Discrete geometry. Discrete geometry explores structures made of isolated points and whole numbers, often organized in grids or lattices, which fundamentally differs from the continuous lines and shapes of traditional geometry. This branch of mathematics underpins practical applications in diverse fields like coding theory and the design of scientific experiments. An intriguing concept within this domain is the idea of visible lattice points. From an origin, a ray of light will distinctly hit lattice points x, y only if their coordinates are relatively prime, meaning they share no common factor beyond 1. These initial points act as primal anchors, effectively obscuring all other integer coordinate points that lie further along the same trajectory. Pick's theorem offers a remarkably simple and elegant method for calculating the area of any polygon drawn directly onto a lattice grid. This area is precisely determined by merely counting the number of lattice points lying on the polygon's boundary, B, and the number of points contained within its interior, C, using the formula area equals B over 2 plus C minus 1. This theorem beautifully demonstrates the unexpected utility and charm of discrete structures. Further showcasing the unique properties of discrete systems is the Fano plane, a prime example of finite projective geometry. This abstract structure comprises just 7 points and 7 lines, one of which is imaginatively depicted as a circle. It embodies a profound duality. Any two distinct points define a unique line, and conversely, any two distinct lines intersect at a unique point. This inherent symmetry sharply distinguishes it from Euclidean geometry, which notably permits parallel lines. The Fano plane holds significant importance as a foundational model, particularly in the theory of experimental design, where it is known as a Steiner triple system. Bridging the realms of continuous and discrete geometry are Pascal's and Bryanson's theorems, a powerful and deeply related dual pair. Pascal's theorem, discovered by Blaise Pascal at just 16, dictates that for a hexagon inscribed within a conic section, like an ellipse, the 3 intersection points formed by extending its opposite sides will always lie on a single straight line.
Its dual, Bryan-Shaw's theorem, asserts that for a hexagon circumscribing a conic, the lines connecting its opposite vertices will invariably converge at a single point, illustrating the deep symmetries and interconnectedness in projective geometry.
29. Graphs. Mathematics often presents two distinct forms of graphs. One familiar type involves plotting curves that illustrate relationships between variables like x and y. The other, a more contemporary field, connects discrete points with lines, forming what we now know as graph theory. This modern approach to graphs found an early and celebrated application in the city of Königsberg, renowned for its 7 bridges spanning the river Pregel. In the 18th century, the mathematician Leonhard Euler tackled a perplexing question. Could one embark on a walk through Königsberg, crossing each bridge exactly once without retracing any steps? The starting and ending points could differ. Euler's ingenious solution, presented in 1735, laid the foundation for modern graph theory. He abstracted the problem, representing land masses as points and the bridges connecting them as lines. The physical lengths or shapes of these lines became irrelevant. Only the connections mattered. Euler observed that for such a walk to be possible, every piece of land entered via a bridge, except for the starting and ending points, must also be exited via a different, unused bridge. Translated into the abstract language of graphs, this means that the number of lines, bridges, meeting at any given point, landmass, must be even, with the exception of at most 2 points, which would serve as the start and end of the unique traversal. The number of lines incident on a point is called its degree. Thus, Euler's theorem states that the bridges of a town can be traversed exactly once if, apart from at most 2, all points have an even degree. Applying this to Königsberg, all its land masses had odd degrees, proving such a walk impossible. However, hypothetically adding bridges could alter the degrees, potentially making such a unique traversal feasible. Another foundational principle is the handshaking theorem, which posits that in any graph, the number of points with an odd degree must always be an even number. One cannot, for instance, draw a graph with only 3 odd degree points. This theorem is intuitive. Every line in a graph connects 2 points, effectively contributing to 2 degrees. If one sums the degrees of all points in a graph, the total must be an even number. Consequently, the sum of all odd degrees must also be even, which is only possible if there is an even number of points with odd degrees. Graph theory also explores graphs that cannot be drawn on a flat surface without lines crossing. These are called non-planar graphs. A classic example is the utilities problem. Connect 3 houses to 3 utilities, gas, electricity, water, without any connections crossing. This is impossible. In 1930, Kazimir Kuratowski demonstrated a powerful theorem. A graph is planar if and only if it does not contain the utilities graph or a complete graph of 5 points as a subgraph. A distinct category of graphs, known as trees, are characterized by having no cycles, meaning there is no way to start at a point and return to it via a different path. Computer directory structures offer a familiar example of a tree graph, with a root directory branching into subdirectories, but no paths looping back without going through the root. 19th century mathematician Arthur Cayley pioneered the work of counting how many different types of trees could be formed from a specific number of points. While computational complexity limited his manual efforts, his research had significant practical applications, particularly in chemistry, where the distinct arrangements of atoms in molecules, which can be modeled as trees, dictate a compound's properties, allowing for the prediction of new chemicals.
30. The 4-color problem. Imagine the seemingly simple task of coloring a map so that no two adjacent regions, those sharing a common border, bear the same hue. This straightforward instruction forms the basis of one of mathematics' most enduring and perplexing challenges, the four-color problem. The question arose from the observation that three colors often proved insufficient to distinguish all contiguous territories, yet cartographers had long relied on the belief that four colors were always enough for any map drawn on a flat surface. Could this practical convention be rigorously proven? The problem first gained mathematical attention in the mid-19th century, when Augustus de Morgan's student Frederick Guthrie posed it, sparking de Morgan's imagination. Early attempts at a solution were made, with notable figures like Charles Sanders Peirce and Arthur Cayley contributing to its spread and initial analysis. In 1879, Alfred Bray Kemp announced a proof, earning him acclaim. Yet a decade later, Percy Heawood exposed a critical flaw in his argument. While failing to prove the four-color theorem, Heawood successfully demonstrated that five colors were always sufficient, leaving mathematicians in a quandary. Was the true minimum 4 or 5? Heawood also extended the problem to more complex surfaces, proving that 7 colors were necessary and sufficient for maps on a donut-shaped surface, a torus. For over a century, the finest mathematical minds grappled with the elusive proof. Incremental progress, such as showing 4 colors sufficed for maps up to a certain number of regions, indicated a path forward. The breakthrough arrived in 1976, when Wolfgang Haken and Kenneth Appel, leveraging the computational power of an IBM 370 computer, demonstrated that 4 colors indeed suffice for any map. Their method involved reducing the infinite number of possible map configurations to a manageable, albeit large, set fewer than 1,500 that the computer could systematically check. This pioneering computer-assisted proof, while celebrated for solving a venerable problem, also ignited fierce debate within the mathematical community. Critics questioned its checkability, arguing that a proof too long and complex for human verification, relying on thousands of lines of computer code, lacked the traditional aha moment of elegant insight. Despite the skepticism, no counterexample has ever been found, solidifying the Appel-Haken result and forever altering the discourse around what constitutes a valid mathematical proof, while also spawning significant advancements in graph theory. 31. Probability. Our daily language is filled with inquiries about chance, likelihood, and probability, terms that underpin the mathematical theory of probability. This field is crucial for understanding uncertainty and evaluating risk. The central challenge lies in quantifying probabilities, especially when outcomes aren't immediately clear. Consider the simplest case, flipping a fair coin. Intuitively, we assign a probability of 1/2, or 0.5, or 50% to getting ahead, assuming its two sides are equally likely. This highlights two main approaches to assigning probabilities: the symmetry approach, where outcomes are inherently balanced, and the relative frequency approach, observing outcomes over many trials. However, applying this to complex situations like predicting tomorrow's snowfall becomes more nuanced. While we might not pinpoint an exact number, we can usefully ascribe a degree of belief, knowing that mathematically, probability is measured on a scale from 0, impossible, to 1, certainty. The mathematical theory of probability gained prominence in the 17th century through correspondence between figures like Blaise Pascal and Pierre de Fermat, prompted by gambling puzzles from Antoine Gombeau, the Chevalier de Marais. His famous question challenged the prevailing wisdom. Which is more probable, rolling at least 1 6 in 4 throws of a single die, or rolling at least 1 double 6 in 24 throws with 2 dice?
Counterintuitively, calculations revealed that the chance of at least 1/6 in 4 throws, approximately 0.5177, is slightly higher than the chance of at least 1/6 in 24 throws, approximately 0.4914. This demonstrates how intuition can often mislead without rigorous analysis. The principles derived from such puzzles are evident in games like craps. When 2 dice are thrown, there are 36 possible outcomes, forming a sample space. An event like rolling a sum of 7, for example, 1/6, 2/5, etc., has 6 combinations, yielding a probability of 6/36, or 1/6. Similarly, rolling a sum of 11 has 2 combinations, a probability of 2/36, or 1/18. In craps, a natural win, sum of 7 or 11, has a probability of 8/36. Conversely, craps, sums of 2, 3, or 12, results in an immediate loss with a probability of 4/36. Other sums lead to a second stage of play. Casinos translate these into odds. For instance, the odds against winning on the first throw are 28-8, or 3.5-1. The concept of exceedingly low yet non-zero probability is vividly illustrated by the monkey on a typewriter thought experiment. Imagine a monkey randomly hitting keys on a typewriter with 30 possible characters. The chance of it typing a specific short sequence, like to be or, is incredibly minute. For this 8-character sequence, there are 38 possible combinations, making the probability 1 in over 650 billion. Even typing once per second, the monkey would take around 20,000 years on average to achieve this specific sequence. While theoretically possible for a monkey to type the works of Shakespeare, the practical timescale renders it absurd, underscoring that minuscule probabilities rarely materialize in human experience. The mathematical foundations of probability were solidified in 1933, when Andrei Kolmogorov defined them axiomatically, much like geometry. These core axioms state that the probability of all possible occurrences sums to 1. Any probability value must be greater than or equal to 0, and for mutually exclusive events, their probabilities can simply be added. From these fundamental principles, the vast applications of probability unfold. From risk analysis and finance to sports, sociology, psychology, and engineering, modern life relies heavily on this discipline, turning gambling curiosities into a cornerstone of scientific and practical understanding. 32. Bayes' theory. The enigmatic Reverend Thomas Bayes, an 18th-century nonconformist minister and mathematician, profoundly shaped our understanding of probability. His posthumously published Essay Towards Solving a Problem in the Doctrine of Chances introduced a groundbreaking formula for inverse probability and the fundamental concept of conditional probability, which forms the bedrock of Bayesian statistics. This approach contrasts sharply with frequentist statistics by incorporating subjective degrees of belief as quantifiable probabilities, rather than relying solely on observed frequencies derived from hard data. Conditional probability describes the likelihood of one event occurring given that another event has already happened. For instance, in a medical diagnosis, consider the probability of a patient having spots given they have measles. This is distinct from the probability of a patient having measles given they have spots. Bayes' formula provides the mathematical framework to transform one of these conditional probabilities into the other, enabling us to update our beliefs as new information emerges. The essence of Bayes' theory lies in using this formula to revise initial probabilities, known as prior probabilities, in light of new evidence, yielding updated probabilities called posterior probabilities. Whether diagnosing an illness or assessing guilt in a courtroom, the Bayesian method allows for a systematic adjustment of one's confidence. For example, a juror's initial low assessment of a suspect's guilt can increase significantly when new incriminating evidence is introduced, provided the evidence's likelihood differs substantially depending on guilt or innocence.
This framework offers a robust way to deal with uncertainty, providing a pragmatic tool across science to law. 33. The birthday problem. Imagine encountering a small gathering of just 23 individuals. It seems astonishing, yet the odds are better than even that 2 people in this group share the same birthday. This counterintuitive truth, known as the birthday problem, confounds many, including seasoned experts, by revealing how quickly probabilities can accumulate. To grasp this phenomenon, consider the certainty. In a room of 366 people, ignoring leap years, it is absolutely guaranteed that at least 2 individuals share a birthday. This is a straightforward application of the pigeonhole principle. If there are more pigeons, people, than pigeonholes, days in a year, some holes must contain more than one pigeon. However, the classic birthday problem addresses a different, more subtle probability. The calculation unfolds by considering the likelihood that no one shares a birthday. If the first person has a unique birthday, the second has 364 out of 365 chances to have a different one, the third 363 out of 365, and so on. Multiplying these decreasing probabilities reveals that for 23 people, the chance of no shared birthdays drops just below 50%. Consequently, the probability of at least 2 people sharing a birthday rises above 50%. For a group of 50, this probability soars to 96.5%. It is crucial to distinguish this from the likelihood of someone sharing your specific birthday. If you are Mr. Trevor Thompson, wanting to know the chances of someone else in the room sharing your March 8th birthday, the numbers change dramatically. For a better than even chance that someone shares your specific birthday, a gathering of 254 people is required, a figure more aligned with common intuition. The classic birthday problem simply refers to any pair of individuals sharing a birth date, not a match to a predefined one. The birthday problem has inspired numerous variations, exploring probabilities for 3 people sharing a birthday, requiring 88 people for better than even odds, or for near birthdays, birthdays within a day of each other, needing only 14 people. It extends to scenarios involving specific demographics, like an equal number of boys and girls, where 32 students, 16 of each, would give a better than even chance of a boy and a girl sharing a birthday. Underlying these calculations is the assumption of a uniform distribution of birthdays throughout the year, an approximation close enough for practical application, despite minor seasonal variations. Fundamentally, these are occupancy problems, mathematical frameworks for distributing balls, people, photons, diseases into cells, days, energy levels, geographical areas, with applications spanning physics, like Bose-Einstein statistics, and biology, modeling epidemics, illustrating how seemingly simple coincidences unveil profound mathematical principles. 34. Distributions. The world around us, from the macabre statistics of cavalrymen struck by horse kicks to the prevalence of specific words in literature, holds patterns that can be understood and even predicted. These underlying structures are revealed through probability distributions, which map the likelihood of various events occurring. When we deal with distinct, separable outcomes, like a count of deaths or the specific first digit of a number, we are observing a discrete distribution. Pioneers like Ladislav Bortkief, Frank Benford, and George Kingsley Zipp each uncovered fascinating insights into these quantifiable arrangements, demonstrating how seemingly random phenomena often adhere to precise statistical laws. Bortkief's enduring scientific curiosity led him to analyze mortality tables, famously examining the number of Prussian cavalrymen who died from horse kicks. Over 2 decades and across 10 corps, yielding 200 core years of data, he compiled the occurrences of these rare and tragic events. To model such infrequent happenings, statisticians employ the Poisson distribution, a powerful theoretical technique. This distribution relies on the average rate of occurrence, lambda, and fundamental mathematical constants to predict the probability of a given number of events. Bortkieff's empirical findings closely aligned with the Poisson distribution's predictions, showcasing its ability to forecast the frequency of rare incidents without direct observation. Another intriguing pattern emerged from Frank Benford's work on first digits. While the last digits in a sequence of numbers, like phone numbers, tend to be uniformly distributed, Benford, rediscovering an observation by Simon Newcomb, found that the first digits in many natural datasets, such as stock market figures, house numbers, populations, or river lengths, are not. Instead, the number 1 appears as the first digit roughly 30% of the time, followed by 2 around 18%, and so on. This non-uniformity, known as Benford's law, is independent of measurement units and holds significant practical value, notably in detecting accounting fraud where fabricated numbers often deviate from this expected distribution. Finally, George Kingsley Zipp, a philologist, delved into the frequencies of words. His investigations revealed that the rank of a word in terms of its popularity directly influences its occurrence. For instance, in English, the most common word, the, appears approximately twice as often as the second most, of, and thrice as often as and. Zipp's law provides a formula that relates a word's rank to its percentage of appearance in a text, with a factor k depending on the author's vocabulary size. This means authors with smaller vocabularies will use common words like the even more frequently. These varied distributions, Poisson for rare events, Benford for first digits, and Zipp for word frequency, equip statisticians with an array of tools to analyze and predict a vast spectrum of human and natural phenomenon, moving beyond guesswork to informed foresight. 35. The normal curve. The normal curve, often recognized by its distinctive bell shape, holds a foundational position in statistics, akin to the straight line in geometry. While its mathematical formula prescribes a single humped curve that gently tapers on either side, raw data rarely conforms to it perfectly. Its importance stems more from its theoretical power and widespread applicability. Pioneers like Abraham de Moivre explored its connection to chance in the 18th century, followed by Pierre-Simon Laplace and Carl Friedrich Gauss, who applied it to astronomical error analysis. Later, Adolphe Quetelet utilized it to study human variations, measuring divergence from the average man in sociological contexts, reflecting a prevailing belief that many natural phenomena were inherently normal in this sense. A vivid illustration of the normal curve's power emerges from the central limit theorem. Imagine Georgina, a human resources manager, surveying her colleagues about their daily travel distance to work. Individual distances varied wildly, and a histogram of this raw data showed no consistent pattern. Yet, she found the average distance for her entire company, the population mean, denoted as mu, was 20 miles. The variability in these distances is captured by the standard deviation. The central limit theorem reveals that even if the individual travel distances themselves aren't normally distributed, the averages of multiple random samples taken from these employees will approximate a normal curve. This distribution of sample averages, x bar, will be centered precisely on the population mean. Mu equals 20. This remarkable principle allows statisticians to accurately estimate population averages from relatively small samples, with larger samples, n, yielding more precise estimates because the variability of the sample averages decreases, sigma over square root n. Beyond estimating population means, the normal curve also effectively approximates other distributions under specific conditions. Consider a simple experiment, tossing a coin 4 times. The probabilities of obtaining a certain number of heads follow a binomial distribution, which accounts for 2 possible outcomes, heads or tails. However, when the number of coin tosses, or trials, n, becomes large, say 100 tosses, this binomial distribution can be closely approximated by a normal bell-shaped curve. In this scenario, we would expect a mean, mu, of 50 heads with a standard deviation, sigma, of 5. This approximation allows statisticians to calculate the likelihood of outcomes for large numbers of trials, such as the probability of getting between 40 and 60 heads in 100 tosses, which is surprisingly high at 95.45%. This demonstrates the normal curve's versatility in simplifying complex probability calculations for numerous real-world phenomena.
36. Connecting data. Data often appears to have intricate relationships, and understanding these connections is fundamental to statistical analysis. While often discussed together, correlation and regression serve distinct yet complementary purposes, much like a horse and carriage, each performing its own vital role. Correlation quantifies the extent to which two quantities, such as a person's weight and height, are related. Regression, on the other hand, provides a powerful tool for predicting the value of one property based on another. The concept of correlation was initially termed correlation by Francis Galton in the 1880s, reflecting its meaning more directly. Galton, known for his penchant for measurement, applied this idea to various pairs of variables, such as the wing and tail lengths of birds. The Pearson correlation coefficient, named after Carl Pearson, quantifies this relationship on a scale from -1 to +1. A high numerical value, like +0.9, indicates a strong correlation, signifying that the data points tend to align along a straight line. Values near 0 suggest little to no correlation. For instance, plotting monthly sales of sunglasses against ice cream sales in San Francisco would likely show a strong positive correlation, where increased sales in one often coincide with increased sales in the other, forming a line trending upwards to the northeast. However, a strong correlation does not equate to causation. It is crucial to use the term association and be cautious about claiming cause and effect based solely on numerical evidence. In the sunglasses and ice cream example, it would be absurd to suggest that buying sunglasses directly causes more ice cream to be sold. Instead, a hidden intermediary variable, such as seasonal weather, hot summer months, links both sales figures. There's also the risk of finding high correlations with no logical or scientific basis at all, like a spurious connection between house numbers and the combined ages of a household's occupants. Correlation can also be adapted for ordered data, where the sequence or rank is important, rather than specific numerical values. Spearman's correlation coefficient, developed by Charles Spearman in 1904, measures the level of agreement between two sets of ranks. For example, when two ice skating judges independently rank 5 competitors, Spearman's coefficient can quantify how closely their subjective evaluations align, providing a numerical measure of their consensus. Beyond understanding relationships, regression enables prediction. Galton's pioneering work in the 1880s on the heights of parents and their offspring revealed a profound principle. Children of exceptionally tall parents tended to be taller than average, but not as tall as their parents, while children of shorter parents were taller than their parents, but still below average. This phenomenon, dubbed regression to the mediocrity, or mean, highlights a natural tendency for extreme values to move closer to the average over subsequent observations. Today, regression is a widely applicable technique for forecasting. Imagine a retail chain wanting to estimate staffing needs for its stores based on customer volume. By observing a sample of stores, plotting customer numbers, the explanatory variable, against staff numbers, the response variable, a regression line can be calculated. This line of least squares best fits the data and always passes through the average point of both variables. The resulting regression equation, like y hat equals 20.8 plus 3.2x, allows the team to predict the estimated staff, y hat, required for a store with a given number of customers, x, making it a highly practical tool for operational planning.
37. Genetics. Genetics, a core branch of biology, profoundly intertwines with mathematics, each discipline enriching the other. At the heart of human inheritance lies Gregor Mendel's theory, which posits that hereditary characteristics, like eye color or blood type, are determined by independent factors or alleles of a gene. For instance, eye color might be influenced by a dominant B factor for brown and a recessive B factor for blue. Individuals carry two such factors, forming genotypes like BB, BB, or BB. Early in the 20th century, a crucial question arose. Would dominant traits eventually overpower and eliminate recessive ones? The answer, a firm no, was provided by the Hardy-Weinberg law, a powerful application of basic mathematics to population genetics. Developed independently by mathematician G.H. Hardy and physician Wilhelm Weinberg, this law demonstrates that in a large, randomly mating population, the proportions of genotypes, and thus observable traits, stabilize after just one generation, remaining constant thereafter. For example, if a population initially has certain percentages of BB, BB, and BB genotypes, these percentages will shift in the first generation but then hold steady for all subsequent generations, preventing recessive traits like blue eyes from vanishing. While elegant and foundational, the Hardy-Weinberg model makes simplifying assumptions, disregarding factors like gene mutation or genetic drift. Consequently, it describes genetic stability rather than the mechanisms of evolution. Nevertheless, it unified Mendelian inheritance with Darwinian natural selection, laying groundwork that pioneers like R.A. Fisher expanded upon. The discovery of DNA's double helix structure later provided the physical basis for genes, requiring advanced mathematical models to describe its geometry and understand complex genetic interactions. Mathematics remains indispensable, not only in modeling genetic processes, but also in inspiring new branches of abstract algebra.
38. Groups. The pioneering work of mathematician Évariste Galois, though tragically cut short, introduced group theory, a powerful mathematical framework for quantifying symmetry. This mathematical concept is crucial not only for understanding pattern, but also as a binding element in theories striving for a unified theory of everything. Symmetry exists in various forms, primarily mirror and rotational. Mirror symmetry describes objects identical to their reflection. Objects whose mirror image is distinct are termed chiral, a concept with profound implications in fields like chemistry, where enantiomers of the same molecule can exhibit dramatically different properties. Rotational symmetry means an object appears unchanged after specific rotations. Group theory provides the tools to precisely measure these symmetries, identifying the set of operations that leave an object invariant. These symmetry operations form an abstract group defined by fundamental axioms, an identity element, an inverse for every operation, and associativity. Groups vary. Some are abelian, where the order of operations doesn't matter, while non-abelian groups, like the symmetry group of a tripod with reflections, demonstrate that order can be critical. Smaller groups can exist as subgroups within larger ones, governed by rules such as Lagrange's theorem, which states a subgroup's order must always divide the main group's order. A monumental collective effort, culminating in the enormous theorem in 1983, classified almost all finite groups into 4 primary types. However, 26 unique sporadic groups emerged, defying these classifications. These mavericks are often of immense size, like the monster group, illustrating the vast and sometimes unpredictable landscape of mathematical structures. This classification stands as a testament to collaborative human ingenuity in uncovering profound order.
39. Matrices. The mid-19th century witnessed a mathematical revolution, giving rise to extraordinary algebra through the concept of matrices. Unlike ordinary algebra, which manipulates single numbers, matrix theory allows entire blocks of numbers to be treated as a unified entity. This multidimensional approach offers immense power, enabling vast data sets, like those found in statistics, to be manipulated simply and efficiently. Instead of performing countless individual calculations, matrices allow for single operations, streamlining complex computations dramatically. For instance, consider a company with multiple factories and products. Matrix addition can instantly sum total production across different weeks, while matrix multiplication can simultaneously calculate total profits and storage requirements, even for hundreds of factories and thousands of products. This power stems from the row-by-column method of matrix multiplication, a core feature that allows for simultaneous interconnected calculations. Matrix algebra, however, deviates from its ordinary counterpart in key ways. Crucially, matrix multiplication is not commutative. A times B does not necessarily equal B times A. Furthermore, finding matrix inverses is more complex, and many matrices, unlike ordinary numbers, except 0, simply do not have an inverse. The concept of 1 in ordinary algebra finds its parallel in the identity matrix, but its role in matrix inversion is often unique. Beyond business, matrices are indispensable for analyzing complex networks, such as airline flight paths, where they can model direct connections and predict multi-stop journeys by simple matrix operations. Initially a theoretical curiosity, matrices soon proved to be the indispensable solution for pressing problems across quantum theory and engineering.
40 codes. Codes are essential for both accurate and secret communication, linking Julius Caesar's ancient ciphers to modern digital signals. Errors, from human input to noise on the line, demand robust systems. Early codes like Morse were poor at detecting errors. A mistyped dot could transform cab into FEZ without warning. Mathematical design allows codes to detect and correct errors. A simple binary example demonstrates this. A single-digit code lacks error detection. A two-digit code, for example 00/11, detects single errors but cannot correct them. A three-digit code, for example 000/111, can detect and correct single errors by identifying the nearest valid code word, much like autocorrect. Modern high-performance digital systems, from satellites to deep space missions, use carefully designed, far-apart code words to combat noise, balancing length with transmission speed. Beyond accuracy, codes ensure secrecy. Historical ciphers, Caesar's shifts, Mary Queen of Scots substitutions, or the WW2 Enigma code were vulnerable once their keys were discovered, often via frequency analysis or key transmission. A revolutionary 1970s breakthrough, public key cryptography, allows encryption keys to be publicly broadcast while keeping messages secure. Based on Euler's mathematical theorems, this system relies on a recipient publishing a key derived from multiplying two enormous prime numbers. A sender uses this public key to encrypt their message. Crucially, only the recipient, possessing knowledge of the original prime factors, can calculate the unique private key needed for decryption. The system's security rests on the astronomical computational difficulty of factoring these immense numbers. Should computing power advance, the defense simply involves choosing even larger prime numbers, making it virtually impossible for hackers to unmix these mathematical components.
41. Advanced counting. Combinatorics, often described as advanced counting, delves beyond simple enumeration to explore how objects can be combined and arranged. It poses questions not just of how many, but in how many ways, captivating minds with its accessible yet profoundly challenging problems. This field, while intellectually rewarding, can prove quite addictive. The core of combinatorics often lies in clearly defining assumptions, as illustrated by the classic St. Ives riddle. Without explicit agreement on who is traveling where, the interpretation of how many were going to St. Ives varies wildly. This need for clarity in problem solving has a long history, with similar combinatorial puzzles appearing in ancient texts, like the Rhind Papyrus from 1800 BC. A fundamental tool in this mathematical arsenal is the factorial number, denoted by n factorial. This represents the product of all positive integers up to n, e.g., 5 factorial equals 5 times 4 times 3 times 2 times 1 equals 120. Calculating the number of unique sequences or arrangements, permutations, of n distinct items. Even for small n, factorials grow astonishingly large. When selecting k items from a larger group of n where order matters, the calculation involves multiplying n by successive decreasing integers k times, expressible as n factorial over n minus k factorial. However, if the order of selection does not matter, we are dealing with combinations. To determine the number of ways to choose k items from n without regard to their arrangement, we divide the number of ordered selections by the factorial of k, since each group of k items can be arranged in k factorial ways. This is represented as nck equals n factorial over k factorial times n minus k factorial, a calculation crucial for understanding probabilities, such as the odds of winning a lottery. Modern combinatorics is a dynamic and extensive field, particularly relevant to computer science. Beyond basic counting, it encompasses intricate design problems like Reverend Thomas Kirkman's 15 schoolgirls problem from 1850. This conundrum, requiring schoolgirls to walk in specific groups over a week such that no two walk together more than once, showcases the subject's depth, linking recreational mathematics to advanced concepts like cyclic solutions and Fano geometry. 42 Magic Squares. The realm of mathematics often reveals fascinating patterns, and among the most curious are magic squares. These are squared grids where each cell contains a distinct whole number. The defining magical property is that every horizontal row, vertical column, and both main diagonals sum to precisely the same number. While a single-cell grid is technically a magic square, it offers little intrigue. However, a 2x2 square is impossible. If one were attempted, the requirement for distinct numbers would be violated by the sums across rows and columns. The simplest non-trivial example is the 3x3 magic square, known as the Lo-Shu square. When filled with consecutive numbers from 1 to 9, the sum for each row, column, and diagonal is 15. Through mathematical deduction, one can discover that the number 5 must occupy the central cell. Legend attributes the Lo-Shu square to an ancient Chinese turtle. A systematic approach, like the Siamese method recorded by Simon de la Loubert, provides a reliable way to construct odd-sized magic squares, beginning with the number 1 in the middle of the first row and moving upwards and across. Remarkably, the Lo-Shu square is essentially unique for its size, with all other 3x3 magic squares deriving from it through rotation or reflection. As the grid size increases, the number of possible magic squares explodes. There are 880 distinct 4x4 magic squares and an astonishing 2.2 billion for 5x5 grids. Artists and thinkers have long been captivated by these numerical puzzles. Albrecht Dürer immortalized a 4x4 magic square in his 1514 engraving Melancholia. Dürer's square not only sums to 34 across all rows, columns, and diagonals, but also across its internal 2x2 subsquares, even incorporating the year of its creation into the bottom row. Benjamin Franklin, a keen amateur mathematician, developed incredibly complex magic squares with intricate symmetries that continue to baffle experts today, demonstrating that the construction of large magic squares is far from serendipitous. Beyond standard magic squares, more exotic variations exist. Squared squares require each cell to contain a different squared number. While a 3x3 squared square remains elusive, the central cell value would be astronomically large, Examples for 4x4 and 5x5 grids have been found, linked to advanced mathematical fields like elliptic curves and quaternions. Mathematicians have also crafted squares where numbers, their squares, and their cubes simultaneously form magic squares or higher powers. Perhaps the most delightful is a 3x3 square by Lee Sallows. If one writes out the numbers in words and then counts the letters in each word, the resulting set of letter counts forms another perfect magic square.
43. Latin squares. The popular puzzle Sudoku offers a glimpse into the mathematical concept of Latin squares. A Latin square is an n by n array where each symbol appears exactly once in every row and every column. Leonhard Euler, who first described them, termed them a new kind of magic square, although unlike magic squares, they are not based on arithmetic and can use any set of symbols, not just numbers. Latin squares prove remarkably versatile in practical applications. For instance, a 3x3 Latin square can elegantly schedule meetings between two teams, ensuring every pair of individuals meets without any time conflicts. Similarly, it can organize discussion topics so each person engages in a different subject with members of the other team. When two Latin squares can be combined to produce a composite where every possible pair of elements occurs exactly once, they are called orthogonal. This property is key to solving complex organizational problems like Euler's historical 9 officers problem. Euler himself conjectured that orthogonal Latin squares did not exist for orders like 6, 10, 14, and so on. While Gaston Terry confirmed this for order 6 in 1900, a groundbreaking discovery in 1960 by Raj Bose, Ernest Parker, and Shara Chandra Shrikande proved Euler wrong for all other such orders. Beyond the trivial cases, order 6 stands as the unique exception where two orthogonal Latin squares cannot be found. The utility of Latin squares extends to scientific research. Statistician R.A. Fisher revolutionized agricultural experiments by using them to manage multiple variables, such as varying soil quality and fertilizer types. By arranging different treatments in a Latin square pattern across a field, researchers can minimize the influence of extraneous factors, like soil variation, ensuring more reliable experimental results. The integration of orthogonal Latin squares allows for the simultaneous control of even more variables, demonstrating the profound practical impact of this seemingly abstract mathematical structure. 44. Money mathematics. Financial puzzles often illuminate deeper truths about money's behavior. Consider the dilemma of a bicycle salesperson, Norman. He sells a bike for £99. A customer pays with a £150 check, and Norman, unable to cash it himself, gets £150 from a neighbor, giving the customer £51 in change. The check bounces, and Norman must repay his neighbor. If the bike originally cost Norman £79, his total loss, the £51 in change, plus the £79 cost of the bike, amounts to £130. This scenario highlights the immediate impact of financial transactions and the value of astute calculation. At the heart of modern finance lie two principal forms of interest, simple and compound. Simple interest is straightforward, calculated solely on the initial principal, yielding a consistent amount each period. Compound interest, however, accrues interest not just on the principal, but also on the accumulated interest from previous periods, leading to significantly faster growth. This interest on interest makes compound interest a powerful force, foundational to savings, investments, and debts like credit cards and mortgages. The compound interest formula calculates an accrued amount, A, based on the principal, P, an interest rate, I, and the number of time periods, N, demonstrating its pervasive influence across financial dealings. The frequency of compounding dramatically impacts growth. An investment compounding weekly, even at a lower nominal rate, can outperform an annually compounded one due to the accelerated generation of interest.
To quickly estimate how long it takes for an investment to double at a given annual interest rate, the Rule of 72 offers a practical shortcut. Simply divide 72 by the annual interest rate. This approximation is useful for rapid financial assessment. Understanding the time value of money is also crucial. A future sum of money is worth less today, a concept known as present value. This calculation determines how much one would need to invest now to reach a specific future amount, considering a given interest rate. Similarly, the regular payments formula addresses situations involving a series of equal payments over time. This applies whether one is saving consistently to reach a future goal, repaying a mortgage through annual installments, or receiving an annuity from a lump sum. These mathematical frameworks empower individuals to navigate complex financial landscapes, from personal savings to significant investments.
45. The diet problem. Dedicated athlete Tanya Smith faces a quintessential resource allocation challenge, meeting her strict monthly vitamin and mineral requirements using two distinct food supplements, Solido and Liqwex, all while adhering to a tight budget. Her predicament vividly illustrates the diet problem, a foundational concept within linear programming, a mathematical discipline developed in the 1940s for optimizing outcomes under constraints. Initially, Tanya seeks combinations of Solido and Liqwex that simply satisfy her coach's nutritional demands. These successful blends are known as feasible solutions. However, her ultimate goal is to identify an optimum solution, a feasible combination that also minimizes her expenditure. Through trial and error, she discovers several feasible options, each with a different cost, revealing the need for a systematic approach. This is where linear programming excels. By visualizing the problem on a graph, Tanya can delineate a feasible region representing all possible combinations that meet her dietary needs. Mathematicians have demonstrated that the most cost-effective or optimal solutions for such problems invariably reside at the corner points of this region. This systematic analysis avoids guesswork, providing a precise, optimal solution based on supplement costs. The historical impact of linear programming is profound. Pioneers like American mathematician George Danzig with his simplex method and Soviet mathematician Leonid Kantorovich independently developed theories that transformed resource allocation, earning them a Nobel Prize. What began as a tool for diet optimization or wartime logistics now tackles problems with thousands of variables across industries, from manufacturing to transportation, demonstrating the enduring power of structured mathematical thought.
46. The traveling salesperson. The traveling salesperson problem, TSP, challenges us to find the most efficient route, visiting multiple locations and returning to the start. For someone like salesperson James Cook, this means optimizing mileage or travel time. A simple approach, the greedy method, always chooses the nearest unvisited city. While improving over random routes, this method often misses the true optimum, because local, immediate gains don't always align with the best overall path. While brute force listing works for a few cities, it quickly becomes impossible. With 13 cities, a computer would take centuries due to factorial growth in route options. This illustrates computational complexity. Problems whose solution time grows exponentially are intractable. The problem's nature also shifts if optimizing for distance, often Euclidean, versus time, where, for instance, a flight via a hub might be faster than a direct, shorter route. Computational complexity distinguishes problems. P-problems are those solvable in polynomial time, efficiently, while NP problems have solutions verifiable in polynomial time even if finding them is hard. TSP is an NP problem, as checking a route is quick. The crucial million-dollar P versus NP question asks if all problems whose solutions are easily verifiable can also be easily solved, shaping the future of computing. 47. Game theory. Game theory, a framework for analyzing strategic interactions, was profoundly shaped by John von Neumann, a brilliant mathematician. Alongside Oscar Morgenstern, he formalized the theory of two-person zero-sum games, where one player's gain is precisely the other's loss, precluding any benefit from cooperation. A payoff table illustrates potential outcomes, and players often employ a minimax strategy, choosing the action that maximizes their minimum possible gain, or, equivalently, minimizes their maximum potential loss, assuming the opponent acts optimally. John F. Nash expanded game theory beyond these competitive scenarios, earning a Nobel Prize for his work. He considered games with more than two players, and situations allowing for cooperation, introducing the concept of the Nash equilibrium. This describes a stable state where no player can improve their outcome by unilaterally changing their strategy, assuming others maintain theirs. Some games feature a saddle point equilibrium, where both players' minimax strategies converge to a single, predictable outcome, rendering the game determined. For repetitive games, like paper, scissors, stone, which lack a saddle point, von Neumann's mixed strategy suggests choosing actions randomly based on probabilities to prevent opponents from predicting play. However, human psychology often introduces a layer of tactical unpredictability beyond pure chance. Not all games are zero-sum. The Prisoner's Dilemma famously illustrates this. Here, individual rational choices can lead to a collectively suboptimal outcome, highlighting the tension between self-interest and the potential for mutually beneficial cooperation. 48. Relativity. Classical physics, developed by figures like Galileo and Newton, understood motion as entirely relative. An object's speed is measured against an observer's frame of reference. For instance, a person moving within a vehicle has a speed relative to the vehicle and a different speed relative to the ground. In this traditional view, time was considered an absolute, universal quantity, flowing uniformly for everyone, regardless of their motion. However, experiments, notably by Albert Michelson in the late 19th century, revealed a perplexing truth. The speed of light remains constant for all observers, irrespective of their own motion or the light's direction. This observation fundamentally challenged the classical understanding of how velocities combine and necessitated a new framework. Albert Einstein provided this revolutionary framework in 1905 with his special theory of relativity. His theory rests on two elegant postulates. First, the speed of light, c, in a vacuum, is invariant. It is the same for all inertial observers. And second, the laws of physics are identical for all observers moving at constant velocity relative to each other. From these principles, Einstein deduced the Lorentz transformations, demonstrating that space and time are inextricably linked and relative to the observer's motion. A profound consequence of this interdependency is the equivalence of mass and energy, encapsulated in the iconic equation E equals mc squared. While Newtonian mechanics remains a highly accurate approximation for everyday slow-speed phenomenon, Einstein's special relativity becomes essential for understanding dynamics at speeds approaching the cosmic constant of light. A decade later, Einstein expanded his insights with the general theory of relativity. This theory extended the principles of relativity to include accelerating frames of reference and, most remarkably, gravity. General relativity redefined gravity not as a force, but as the observable effect of mass and energy curving the very fabric of a four-dimensional spacetime continuum. This elegant model accurately predicted phenomena such as the bending of light by massive objects and the subtle precession of Mercury's orbit, explanations that had eluded Newtonian gravitation. Einstein's work thus not only unified seemingly disparate phenomenon, but also profoundly shifted our perception of the universe. 49. Fermat's last theorem. Fermat's last theorem presents a profound mathematical puzzle.
While two square numbers can readily sum to a third square, a concept known through Pythagorean triples, like 3 squared plus 4 squared equals 5 squared, the same does not hold true for higher powers. Specifically, it states that for any integer exponent n greater than 2, there are no positive whole numbers x, y, z that can satisfy the equation xn plus yn equals zn. This elusive principle falls within the realm of Diophantine equations, which are characterized by their demand for whole number solutions. The theorem's journey through history is rich with attempts and near misses. Pierre de Fermat, a 17th-century French mathematician, famously noted in the margin of a book that he possessed a truly wonderful proof but lacked the space to write it. For over 3 centuries, this tantalizing claim inspired generations of mathematicians, including notable figures like Euler, Legendre, and Kummer, to seek a general proof or to prove the theorem for specific exponents. Despite numerous partial successes and even a prize from the French Academy of Sciences, a universal proof remained out of reach, inspiring countless false claims and advancing abstract algebra through these very failures. The ultimate resolution arrived in 1995, delivered by Andrew Wiles, after nearly 8 years of dedicated, solitary work. Wiles's monumental proof ingeniously connected Fermat's last theorem to complex concepts within the theory of elliptic curves and the Taniyama-Shimura conjecture. After an initial version was found to have a flaw, Wiles, with the aid of a colleague, successfully rectified it, finally settling one of mathematics' most celebrated and enduring mysteries.
Chapter 50: The Riemann Hypothesis. The Riemann hypothesis stands as one of pure mathematics' most formidable unsolved challenges, holding the key to unraveling the mysterious distribution of prime numbers. This profound problem finds its roots in the behavior of infinite series. Consider the harmonic series, 1 plus 1/2 plus 1/3, etc., which, despite adding ever smaller fractions, slowly but unboundedly diverges to infinity. In contrast, the series formed by squaring the denominators, 1 plus 1/4 plus 1/9, etc., rapidly converges to a specific finite value, pi squared over 6. The critical difference between these two behaviors lies in the exponent of the denominators. This distinction leads to the Riemann zeta function, z of s, a generalization where s represents the exponent. Crucially, when s is extended to complex numbers, the function possesses zeros, specific values for which z of s equals 0. Riemann conjectured in 1859 that all its non-trivial zeros lie precisely on the critical line where the real part of s is 1/2. Billions of zeros have been numerically verified on this line, yet a rigorous proof remains elusive. The hypothesis's deep connection to prime number theory, recognized by mathematicians like David Hilbert, underscores its immense importance and the million-dollar prize awaiting its resolution. That wraps up our exploration of today's book. If even one idea here gave you something to reflect on, give it a like so YouTube knows to share more with you. And if you'd like the next insight in your feed, hit subscribe. Remember, what you heard today is our independent interpretation, enriched with analysis and exercises. The full book has far more depth, so consider reading it to experience the author's work directly. Thanks for listening to Def Do Insights, where we turn great books into tools for growth.